Thank you, everyone, for taking the time to join me today to discuss reheat furnace mixed gas pressure control and how REXA can improve the performance of your actuators at your plant. My name is Mark Farah. I handle metals and mining industry for REXA, so I am pleased to have the opportunity to introduce our technology to you. For some of you attending, you may have experience with our product, so parts of this presentation will be a great refresher. For those new and looking to gain a better understanding of electrolytic technology, I'm confident you will find the webinar to be informative and gain valuable insight on REXA. So let's begin. For the webinar agenda, the topics we will be going over will include key results, a summary of operational improvements made at a large integrated mill, actuator types. To better understand the REXA technology, we need to look at other types of actuation to distinguish them from what we do. It was from the need to combine the benefits of each type of actuation technology that REXA originates and eventually took shape. In order for the plant to operate efficiently and in safe operation, it's important that the valve reduces the pressure prior to the burners in various heating demand conditions. We'll touch on many of these requirements. And finally, we'll wrap up the webinar with some takeaways and answer a few questions. Please share your thoughts throughout the webinar. So let's get started by defining what an actuator is. The Emerson Control Valve Handbook states that an actuator is a pneumatic, hydraulic, or electrically powered device that supplies force and motion to open and close a valve or damper. Today we will discuss the role an actuator can have on a reheat furnace operation. The purpose of the reheat furnace is to control the heating and cooling of metal parts for the purpose of altering their properties. The location of the retrofit is a Jamshedpur integrated mill in India. Established in 1907 as India's first integrated steel plant, Jamshedpur Works currently comprises of a 9.7 metric tons per year crude steel production facility and a variety of finishing mills providing high quality steel for the automotive, construction, and household appliance markets. The reheat furnace is located at the hot strip mill and is the process step before hot rolling. After monitoring the mixed gas pressure entering the reheat furnace, the rolling mill operations team found the operational results to be increasingly disappointing. A large part of the problem was traced to the inability of the pneumatic actuator to reliably control the valve to position. Unfortunately, even with the use of a smart positioner, the pneumatic actuator lacked precision due to the compressibility of air. In June of 2016, plant operations chose to retrofit their existing pneumatic actuator for REXA electrolytic actuator. Immediately, the customer noticed an improvement of mixed gas pressure range. There was a pressure variation reduction from 150 millimeters water column with pneumatic to 20 millimeters water column with REXA. The actual process trends are easier to quantify with this chart. Both the head of the fuel management and head of hot strip mill at Tata confirmed the significant improvement with REXA. The benefits for lower furnace temperature variation, less fuel used, and easier operations. No need to shut down burners manually. I want to now relate the functionality of an actuator to the human body. The brain or controller communicates via nerves or transmitters once the body's sensors, such as eyes or the nose, detect environment conditions. When the controller determines the appropriate correction signal, the actuator is the required muscles to position the valve. In terms of responding to the correction signal, controllers do not control. They make decisions and send commands to final control elements. Sensors do not control, they sense. They see, feel, or measure pressure or temperature in the process. Control valves do not control, they simply act as an adjustable orifice in a pipe. Actuators are the final control element that physically makes these adjustments. They are the muscles of the process plant. So the current state of actuation, pneumatic actuators are soft and pushed around, their speed is slow, and their sizes can be very large. The diet for electricity is large, continuously consuming power and air. Finally, they can't get comfortable and stable, continuously twitching due to friction changes. What we are interested to achieve in state-of-the-art actuation is stiff or rock-hard positioning. They can't get pushed around. Must be quick and accurate when the control set point changes. Be able to run efficiency with low power consumption, that is, live on a low-calorie diet. Finally, they must be smart such that positioning can be configurable with detailed diagnostics of system or body health. For an actuator to perform at a high level in the most challenging applications, it should have the following DNA. It should be reliable with low scheduled maintenance, precise control of the process variable, and be intelligent with diagnostics and digital communications. Unfortunately, one cannot get all these items at low cost. There are three types of actuator technologies: pneumatically driven, mechanically driven, and hydraulically driven. Each uses a different method to develop forces and create motion, all with advantages and disadvantages. First, pneumatic actuators are most common on control valves on new equipment and projects. Their advantages include low purchase price and they have fast stroking speeds. However, there are limitations of using pneumatics. Because air is a compressible fluid medium, it tends to build up in order to create motion. The results are losses in resolution, overshoot or undershoot, and increased dead time. Even with the use of a smart positioner, the compressibility of air is an inherent problem to achieve rapid and accurate positioning. Operating costs are expensive when you include air compressor energy, dust filters, and water separators. In cold weather, moisture in the air lines will freeze and make the pneumatic actuator non-functional. This graph shows the positioning performance of a Rexa actuator versus a pneumatic actuator. The changes to the black line control signal are easily followed by the Rexa in green, but with the pneumatic in red, it cannot respond fast enough and often overshoots or is unresponsive to the desired set point. With the deadband set at 0.1%, which leads to a resolution of less than 0.1%, the linear capability of Rexa is less than 0.05%, and the Rexa X-Pack is the only actuator product line truly capable of matching the potential of modern control systems. Next is electromechanical actuation, most commonly found in on-off type service, which provides tighter control and better frequency response than pneumatic actuators, but not hydraulics. These are also good for outdoor service. However, most electromechanical actuators can have limited duty cycle, usually around 20 to 30%, limited force or torque output, and very few fail-safe options available. The use of electrohydraulic actuators are common to control valves for precision. These systems provide high frequency response and great accuracy with the high duty cycle. They're also good for high torque application. These benefits, though, come at a cost. High capital costs, electrical consumption, and maintenance costs add up to offset the positioning benefits. So I like to use analogies. Sometimes they communicate the message or sometimes they just get lost. The control valve is the final control element in many processes to make steel. Often the limitation of installed actuators is that they do not take advantage of today's advanced DCS systems. One analogy I like to use is the need in Formula One racing to push technology and performance between the powertrain and the racing tire design and compound formulation. In 2005, at a Formula One race in Indy, some tires were failing during qualifying laps on turn 13. So the tire manufacturer suggested to have the race car slow down on that turn to keep drivers safe but increase lap times. For a valve actuator assembly controlling gas flow, we do not need to be limited or slowed down such as by a pneumatic actuator. With Rexa, electrolytic performance enables the power of the DCS to be realized. Rexa combines the benefits and capabilities of each of the actuator technologies into one. The simplicity of fail-last position and high duty cycle of pneumatics, intermittent operation of electromechanical, and the positioning accuracy and fast actuation speed of hydraulics. Okay, let's talk about some benefits of electrolytic actuation. To start with, it's a very unique design unlike anything on the market today. The true closed-loop hydraulic system with low oil volumes, approximately 90% less than those found in a standard HPU. Smaller Rexa units have as little as 500 milliliters of oil, which is about 1 can of Coke soda. There are no filters or oil changes required, making it maintenance friendly. All models can operate at 100% duty cycle if needed through the use of brushless DC stepper or servo motors. These units are high precision and repeatable to 0.1% of span. Our modular design allows for a very high thrust and torque output with high-speed fail-safe options. Having Rexa actuators installed at major steel producers around the world, Rexa actuators are unmatched when it comes to being rugged and reliable. The electrolytic technology consists of two primary components, the mechanical subassembly and the electrical subassembly. The mechanical portion is attached to the driven device, which in the case of the mixed gas fuel supply would be a butterfly valve. It contains a motor, pump, flow match valve assembly, cylinder, and feedback housing. The electrical subassembly is basically the positioner for the actuator. This is where the main power supply and control signal are routed, and the origination of 4 to 20 milliamp position feedback for connection to the DCS or other control system. Digital communications such as hard or foundation field bus are also available. We separate the electric and mechanical assemblies for ease of access and operation. There are many severe applications, for example, very close to furnaces, where onboard electronics simply would not survive. The control box can be mounted in a convenient location next to the valve or up to 700 feet away. And operation and ambient temp of the power modules between -40 F and 250 F. Okay, next let's take a closer look at the Rexa hydraulic circuit. This is the real area differentiation with our technology in comparison with HPU-based electrohydraulic systems. The centerpiece of the electrolytic circuit is the bidirectional gear pump, which is coupled to the Rexa brushless motor. The gear pump works in conjunction with the flow match valves, which are designated as flow match valve 1 and flow match valve 2 on the schematic. It is important to note from a size perspective, the flow match valve and the gear pump can each be held in the palm of your hand. During operation, when the actuator is at the desired position, spring-loaded ball checks are locked in place to prevent the flow of oil through the flow match valves. The cylinder is hydraulically locked into place, so forces acting on the valve will not result in valve movement, which is observed in pneumatic actuators. But when there's a signal change, the motor activates, turning the bidirectional gear pump, which instantaneously builds pressure, allowing the ball checks to open. The oil is then transferred through the flow match valve from one side of the cylinder to the other. Once the cylinder has reached its desired set point, the motor stops, the ball checks are seated, stopping the flow of oil through the system. When in standby mode, power draw in the electronics cabinet is only about 70 watts. Motors on the brushless stepper or servo motor style, designed for 100% duty cycle and capable of very high frequency response from 1 to 5. The cylinders that we use are dual rod or rack and pinion, so the oil volume exiting one side of the cylinder is equal to the volume exiting the other side. The design eliminates both the requirement for an external reservoir and the need for continuously circulating oil through the system. This also leads us to another significant benefit of our technology, greatly reduced oil volumes. This is an example of a rotary rack and pinion assembly. The same volume of oil is moved to either side of the cylinder with no reservoir, minimizing oil volume. Rotary units normally use non-contacting feedback coupled to the cylinder output shaft to eliminate lost motion. The cylinder type rack and pinion delivers a constant torque throughout the range moment. The cylinder seals are rated for 2 million full strokes and 20 million dither cycles. The oil level plug indicates the oil level is good for operation. Our focus today is on the reheating furnace to use after continuous casting. Notice all the various end products post-heating that may require high quality, including hot rolled coil and sheet, and also welded pipe. Reheat furnace is an energy-intensive piece of equipment to heat and soak the incoming material, such as a billet, slab, or bloom. The furnace operates at approximately 1200 degrees Celsius. Once heated, hot mechanical deformation steps are used to roll steel to final size and shape. We'll see that accurate and repeatable actuators are key to the reheat furnace's purpose. Mixed gas is a blend of byproduct gases, including blast furnace and coke oven gas, blended together along with other gases to increase calorific value for combustion with air. Mixed gas is used as a fuel source for various plant operations, including reheat furnaces in the rolling mill. The recovery of byproduct gases and their use in subsequent energy processes make the plant more efficient. For anyone that is a firefighter or has taken a plant safety course, this symbol should be familiar. The right mix of air and fuel is the reheat furnace's goal. Stoichiometric simply means that there's enough oxygen to mix with all the fuel so that there's complete combustion. No fuel waste or undesirable products are produced that are harmful to the environment. One challenge is the mixed gas calorific content is relatively low and fluctuates. There are multiple paths of heat loss through the reheat furnace. Opening losses and heat up requires input changes to the manipulated variable to keep the temperature at the target set point. Rexa controls the main gas pressure, and additional pneumatic valves control flow to each burner. The gas pressure requirements are not met. The reheat furnace and post-process step operations can be negatively impacted. The furnace will have higher mixed gas fuel consumption due to incomplete combustion. The reheat furnace pressure will not be consistent and will have temperature and emissions fluctuations. The temperature variation can also increase the burner part lifetime. Reheat furnace operation directly controls austenite grain size. The larger the austenite grain size after reheating, the larger the ferrite grain size downstream. Final ferrite grain size is related to toughness, yield, and tensile strength. In this figure, the austenite grain size and reheat temperature is plotted with various soak times ranging from 10 to 60 minutes. It is important to note that in the target operating range of 1050 C, it is not flat, but the grain size will increase with longer times and higher temperatures. Let's return now to the mixed gas pressure control application at Tata Steel and review more of the retrofit details. So the actuator is a Rexa X2 R10000K model. Its torque of 10,000 pounds-inch or 1130 Newton meter. It has a rotational speed of 18 seconds per 90 degrees, and the fail position is fail in place or fail last. The actuator position is horizontal, and the typical application duty cycle is a minimum of 3 movements per minute, continuous operation. And the actuator is mounted to a butterfly valve, 36 inches or 900 millimeters diameter. Picture on the left is the pneumatic actuator mounted to the butterfly valve. Notice the additional linkages that can contribute to additional hysteresis. The picture on the right is after the retrofit was completed. The Rexa is easily mounted directly to the valve stem, eliminating linkages. The Rexa can be mounted in any orientation. So Rexa actuator takeaways. In summary, the Rexa actuators have provided the following benefits at Tata Jamshedpur: improved reheat furnace operation and reduced pressure variation going to the reheat furnace. The pressure set point was reduced and the pressure range narrowed from 150 millimeters water column to 20 millimeters water column. Improved combustion and reduced emissions. The mixed gas fuel pressure fluctuation was reduced significantly so that the reheat furnace evenly heats the slab. When the water jet is sprayed on it to cut it, the strip comes out cleanly finished for a better quality, requiring less rework. A little bit about Rexa to those unfamiliar. The unique actuator patented concept and company began as a small startup in the early 80s. After trial and error, the first generation model was installed in multiple industries in 2001. In 2008, the X2 generation contained key features and built upon the Quartz technology to make it rugged and reliable. In 2016, the X3 electronic module added additional diagnostics and ease of maintenance. Rexa's rapid and consistent growth continues with over 39,000 actuators and drive units sold worldwide. With headquarters near Boston and a service and distribution center in Houston, Rexa continues to expand and grow, focusing on key industries such as metals and mining, power, and oil and gas. Rexa is an established partner in all the major steel producers in the world. Whether it is an integrated or mini mill, Rexa can solve the toughest steel making applications. I'd like to acknowledge the following individuals in India that worked with the customer to upgrade the actuators at Tata Steel: Sulesh Sharma from Credits Automation and Chintan Chotoi from Site Technologies. Both of their contributions were critical to tell this success story. Thank you very much.